Right. So you remember the problem? Seemed. So we were given a graph, and we were asked to count how many distinct swords there were. And a sword looks like this. There's one vertex of degree 4, one vertex of degree 2, and the others were degree 1 vertices. And this could be embedded anywhere in this graph, and we just had to count the number. The only problematic aspect of the problem is that there are lots of vertices and lots of edges. We're told that there could be up to 100,000 vertices and up to 100,000 edges. This is a real problem. We kind of figured out how to deal with swords. We essentially had to set up a loop to try all possible positioning for the D and all possible positioning for the B, and then that kind of does it for us. So we went through several iterations of this, and you guys remember this. Ultimately, we figured out that we had to do something like this, and then I think we came up with what's pretty close to the last version. And it looked something like this. That said, for every possible positioning of D, hi Daniela, for every possible positioning of B, we do we add up this count, which gave us how you pick 3 possible neighbors of D and multiplied by one of the neighbors of B, which would become A for us, right? So this told us how many different ways we could pick A. The reason it's -1 is because one of the neighbors is D. And then this told us how many different ways we could pick these 3 guys. And I forgot to fix this. This should have been degree D -1, right? So this is where we stopped, and we realized that there is a problem with this. Sorry, Daniela, we are discussing a problem from last time. Maybe you're a little, I don't know if you watched the videos, but this is, hey, hi, come on in. Yeah, this should be degree D -1, but the rest of this is correct, except that it doesn't work under the case when B and D have vertices in common, have neighbors in common. And so this is incorrect if D and B have common neighbors, right? And if they do, we really have to count how many intersections there are, how many common neighbors they have, right? So one way to think about this is you look at the neighborhood of B and you look at the neighborhood of D and find how many of these are in common. So once again, this is sort of what we wrote as the code. Again, this should be degree D -1. If the intersection between the neighborhood of D and the neighborhood of B is empty, if they don't have anything in common, then this formula works out. Otherwise, we have to do something and fix this. So what do we have to fix? And for that, it's a good idea to draw a picture. So here is D. We're assuming that D has fairly large degree. So D has many neighbors. Of these, we are always going to pick 3 as the 3 vertices C, F, and E. We're looking at one of its neighbors, that's B. And again, B has many neighbors. Of these, one of these is going to become the vertex A. The problem, as we said, is when they have a common neighbor, because now we could have chosen this as A, which would decrease the set of choices for D as the neighbors. When that happens, you have to do, so essentially it essentially cuts down the degree of the number of choices for D by 1, and that's all it does. Everything else is the same. So, but then there could be many common neighbors that they have. And all of these are a problem. So you have to count how many common neighbors they have. And if the common neighbors is k, then this is what you get. So let's see what this is. Did I write down what k and k prime are? Let's see if I did. Yeah, if we call the number of common neighbors as k, then something is not right here. I did screw up pretty badly. So let me go try and fix this. So first of all, let me fix this guy here. Hey, hi. We know that there it should be a -1. And then, oh yeah. So this is all pretty correct. Yeah, I think something like this. Let's check if this is right. Yeah. So here's what I'm saying. I'm saying that if there are k common neighbors, right? Let me write this down. If there are k common neighbors, and if the degree of B is that, then one of these simply connects it back to D. K of these are neighbors. So this I'm going to call as k prime. Okay. So what I get is I didn't get that right still. This should also be degree of D minus 2. So right. So if there is a common neighbor, then let's ignore the common neighbors. If it picks one of the neighbors that are not common, then I can pick any 3 from here. So that part is this, because if I don't pick one of the common neighbors, that's k prime, but not -1, then I simply get degree of D -1, choose 3. Of the remaining things here, I can pick any 3 I like. But if I pick one of the common neighbors, then I also have to remove the common neighbor from the set of choices that I have. So if I pick A as the common neighbor, that's going to become A. Then the number of choices goes down by 1. So instead of degree D -1, choose 3, it's going to be degree D -2, choose 3. That's all. And so this gets multiplied by all the things that are not common neighbors. This gets multiplied by all things that are common neighbors, and that's it. Okay, the rest should be as is with no change. Now, we still don't know how to do this because there may be too many of them, and that's our next step. But once we know how many common neighbors there are for any pair of vertices, we'll be done. Okay, that's really the point. So were you here last time? Are you? You were not here? Okay. Sorry? Yeah, it's for something called counting swords. It's from one of the recent competitions. I won't have time to describe the whole thing again, but I'm going to describe this problem. That's a very specific subproblem of that problem, which says, if I gave you a graph, how quickly can you count how many triangles there are? Okay, let's talk about that, because that's the most interesting part of this problem now. So counting triangles simply says, I give you a graph, and your job is to tell me how many triangles there are. Okay? So here, that's a triangle, that's a triangle, that's a triangle, that's a triangle, and maybe that's it. But I can throw in a few more edges, and you'll get a few more triangles. Okay? So question is, how do I do this? Now, the simplest way to do this is, well, first of all, let's ignore that for a second. In order to compute the number of triangles, I can do this in a very trivial way. I can pick every possible set of 3 vertices, right? So there are n vertices. I can simply use combinations to pick every possible subset of size 3 and check if it forms a triangle. So I'll try this, this, and this, that, and that, and so on and so forth, and check if they all form triangles. And for whichever ones form triangles, I'll count 1. Fine? So that's the easy way to do it. Now, what's wrong with this? What's wrong with this is, well, there's nothing wrong with it. It'll work perfectly fine, except that it'll take n cubed time to run, because there are n choose 3 different combinations, and n choose 3 is approximately n cubed. Fine? And since in our problem, n is something like 100,000, n cubed is simply out of the question for us, right? So we want something better than n cubed in order to make this meaningful for us. Now, there are 2 things that you need to remember. One is that you're told that n is up to 100,000, and also the number of edges is at most 100,000. So this is what you're told, okay? So how do I make that to work over here? So let's try the next possible way, and that's the improved way. Any thoughts on this?
You can go through every vertex, look at its, choose 2 of the neighbors.
Yeah.
And do this for every vertex, so you get all of n squared.
Yeah. Yeah. So essentially, you for every vertex, you take 2 of its neighbors and check if they are connected by an edge. Here's another way to do it, which turns out to be exactly the same. You do the calculations for an edge. You start with an edge. For every edge, check if there's some vertex in common. Okay? So find all the vertices that form a triangle, and it'll turn out to be roughly the same as what Ricky just proposed. But at least this will help us to count slightly differently and slightly easily. You'll see that this will take you time m times n. All right? So we can see that given these numbers, we're already better than before, because earlier we were doing n cubed, which will come up to about 10 to the 15. Right? So this would be something like 10 to the 10. So we've already cut down quite a bit. In general, the number of edges can be as bad as n squared or n choose 2. So it may not help in general graphs, but given that information, it turns out that it'll help us a little bit. Okay? Are you okay with this? Now, why is it m times n? Because you have to look at the neighbors of both u and v and figure out what's in common. So essentially, you have to look through all their neighbors. Right? Cool with this? Okay. So we're going to improve this a little bit more. Well, actually, we won't improve this a little bit more. We'll only improve on the analysis, essentially. So let's see what's going to be, what we're going to change. Instead of writing this as find all the vertices that form a triangle with u and v, I'm going to say, let me look at the adjacency list of u and the adjacency list of v, and go through that list and see if there's anything, or find out how many things are in common. If there's anything in common, that's going to form a triangle, right? Remember, you have u here, you have v here. You know that they are already neighbors. We're going to look at all the vertices that U is adjacent to. We're going to look at all the vertices that V is adjacent to. This is your adjacency list of U. This is your adjacency list of V. And we're going to try and see if there's any intersection. For everything that they intersect, you're going to have a triangle. Is that clear? And we'll just count how many intersections there are in those two sets. So how do we do this? Well, if we do this, we could do this in a simple way by taking big O of n time. And that's simply saying, okay, is one, we'll just do a simple sorting and then check them. By the way, you can sort these adjacency lists fast because they are always numbers between 1 and n. So there are simpler ways to sort them. But essentially, you can find this intersection in linear, in big O of n time, which will still be big O of m times n. However, I'm going to try and write this in a different way. I'm going to write this as big O of degree of U plus degree of V. I'm going to look at these two adjacency lists. This adjacency list has how many items? It has degree of this guy, that many items in the list. This guy has, again, as many items as the degree of this guy. And then I'm trying to put them together. What I could do is simply use an array of size n and check whether check how many things there are in common. I can put all the things that are in U in that array, and then when I try to put V, if it's already there, I know that those are going to be overlapped, right? So, so it turns out I can do this job in time exactly degree of U plus degree of V. Does that make sense? Again, let me just show you how this goes. Here is vertex U, and here is the adjacency list for U. You guys remember this kind of picture from your graph theory, graph algorithms days? So here's the adjacency list for U. Here's the adjacency list for V. We don't know how many elements there are. We don't know what elements there are. We don't know in what order they are, but they're given to you, right? So one option is to sort them and then walk through the list. The other option is to create an array, and for every item here, mark all those guys. And then go through this list and see if you're hitting any of those. Okay? And if you hit any of those, you count all the hits that you get. Otherwise, you go back and reset them, and you get the list back for the next kind of check, right? So I can do this work in essentially this guy's length plus this guy's length. That's what I'm trying to say, right? So that's what it says. That's the number of items here is the degree of this guy. Number of items here is the degree of this guy, right? So the time it takes is degree of U plus degree of V, and we do this for every edge in the graph, right? So the time it takes is that. Is that clear? Now, we can simplify that horrible looking thing. How do we simplify it? Well, here's what I do. So I can write down every edge in the graph. So let's say I have an edge from 1 to 3. I have an edge from 2 to 4. I have an edge from 4 to 5. I have an edge from 2 to 5. I have an edge from 6 to 9, and so on and so forth, right? When I process this edge, the time it's going to take me is the degree of 1 plus degree of 3, right? So here it's going to be degree of 1 plus degree of 3. That's the amount of time it'll take me to process that. In order to process this, it's going to be degree of 2 plus degree of 4, and so on and so forth. When I add up all of this, what do I get? Now, degree of 1 is going to show up once for every vertex that's adjacent to 1. So how many times will degree of 1 show up here? Degree of 1 will show up degree of 1 times, right? Same thing with degree of 2, same thing with degree of 3. So therefore, what we get here is that this sum is simply degree of each vertex squared summed over all the vertices. Does that make sense? Yeah? Or was that too fast? Are you okay with this? Stop me here, otherwise there's no point in telling you the next step. Should I go over this again? Yeah, go over it again. Okay, so in order to process one edge, somewhere I pick one of these edges, right? The time it takes for me to process this is proportional to the degree of this plus the degree of this. That's what I know. Well, so in order to process edge 1, 3, it takes me degree of 1 plus degree of 3. I'm going to add up this for every edge in the graph. So next I do this for this edge, then this edge, and then this edge, and then this edge, and so on and so forth. When I add up all of that, what do I get? So this guy, let's say this is vertex 1. This guy shows up for that edge. It also shows up for that edge. It also shows up for all the other edges. And there are as many edges as its degree. So therefore, degree of 1 appears in degree of 1 places in the sum. So therefore, when I add it all up, it's going to be degree of 1 times degree of 1, which is degree of 1 squared. Same thing will happen with degree of 2, then degree of 3. So essentially, I'm saying it's just sum of the squares of the degree. All right? And this we can simplify. Before I simplify that, do you guys know what is the sum of the degrees of a vertex? What does this sum add up to? Twice the number of edges, right? So this is exactly equal to 2m. Why? Because each vertex will show up one time for each of the edges in both directions, right? So because you're looking at the sum of the degrees, that edge will be counted twice, once from this end and one from this end, right? So if you just add up the degrees, you get 2m. But what we really want to do is to sum up the squares of the degrees, which is a little bit worse. So how do I figure this out? Well, not that easy, it turns out. But I'm going to tell you that this turns out to be m times 3/2. And we're going to see why that's so. All right, so now we have to do one more trick. So let's say I write degree of vertex 1 as d1. I write degree of vertex 2 as d2 squared, d2, and so on and so forth. That's what I really want to figure out, right? Now, some of these vertices have low degree. Some of these may have very high degree. We know that not every vertex can be high degree because d1 plus d2 plus d3 is at most 2m. In fact, it's exactly 2m. So therefore, these can't all be very, very high, right? Now, how high can they be? So here's what we're going to do. Let's pick only those guys that are let's only pick things that have degree smaller than square root m. What's going to be their sum? This is going to be m. Let's say most of them, or let's say all of them have degree less than square root m. Then what happens is I can write this as d1 times d1 plus d2 times d2 and so on, dn times dn. If all of them are less than square root m, then one of them if all of them are less than square root m, I'm going to replace this guy by square root m. So that's a larger thing, right? Fine. So then this whole thing is less than d1 plus d2 plus dn multiplied by square root m. But this sum is roughly m. So what you get here is m times square root m, that's 3/2. So if all the vertices have low degree, we're great, right? Then the time is not so bad. By the way, why is this not so bad? Because m is 10 to the 5. What is m to the 3/2? It's going to be 100,000 multiplied by some 300 or so, right? So we're talking maybe 3 million. Did I get that right? No, 30 million. And 30 million can be handled. Okay? So this is all right if m is 100,000. But we only showed that this is okay if all the vertices are of low degree. Now let's say some of them are not. What do I do then? Any ideas?
Like k vertices are going to be less than m, and then n minus k ones are not.
Yeah. But what if that n minus k is too large? So there's this very simple argument that shows that not too many of these values can have large degree because of this guy. How many of these can be larger than square root m? How many times do you have to multiply square root m in order to get at most 2m? Sorry? 4 times. Why 4? I want to know square root m times what gives me 2m. Yeah, so roughly square root m. Well, at least 2 times square root m, fine, right? So this I'm going to call as k. What I'll tell you is that k cannot be bigger than 2 times square root m. So what we're saying is you can't have more than this many vertices whose degree is larger than square root m. Okay, so yeah, there may be some vertices that have large degree, but not too many of them. In fact, there are only square root m such vertices. So let's pick out all those guys that are larger than square root m. The rest must have smaller than square root m, and we know how to deal with them. If it is larger than square root m, let's assume it's as big as n. Okay, but there are only square root of m such guys, so therefore they will all add up to square root m times n. And so therefore, whether you count vertices with high degree or with low degree, the total work that you'll do is only m to the 3/2, and that's manageable. So essentially what we've said is that silly piece of code there should work for you as long as m is only 100,000. Does that make sense? Or was that a bit too much? Cool. So what's the conclusion now? That's how you find the triangles for, well, actually you can do this for every pair of vertices, every edge in the graph, and essentially you plug that into the previous code where we said, sorry, where did that go? Here. So we'll do exactly this, except that for every choice of D and B, their neighbors will find their intersection using the code that we showed a couple slides later, and do exactly this. We'll count how many neighbors they have, and we'll be done. And we know that all of this cannot take more than m to the 3/2. So therefore, this whole code should work pretty quickly and efficiently enough for you to implement. So that's the idea here. Any questions? Even if you didn't understand the analysis, what you need to know is that this code should work for you. That's what's important. Okay? Shall we move on to something else? You guys still look dazed.
The formula is that k is equals to the number of vertices that intersect.
Over here, yeah. If k is equal to 0, you use the first formula, otherwise you use the second formula. Okay? Actually, you can always use the second formula. It's just that when k is 0, everything comes here. Right? Okay. I think I don't, that's the stuff, yeah. Yeah, I think I didn't show the rest of this slide, but it's right here. Yeah, if you look at vertices with low degree, then they only add up to m to the 3/2. If you only look at the vertices with high degree, there are not too many of them, and again, they'll add up to at most m to the 3/2. So both of these, when you add together, it's still m to the 3/2, which is still in pretty good shape. Actually, it's m times n to the half, but that's, since they're both bounded by the same number, you're still okay. Is that clear? All right. Where are we? Okay. So we finished word counting. If you guys, would you like to present for us the I love strings problem? So first explain the problem if you don't mind, and
I have a presentation, I can send it to you. And,
Or you can just bring it over. Do you have a?
I don't have a USB hub. It's only USB-C.
Oh, then just send it to me. Yeah. Then just send me the file. Yeah.
Oh, wait, that's okay.
Oh, you have a converter? Cool, cool. There you go. Thank you. There we go. So there we go.
Okay, so the problem is I love strings, and then this is my solution. First, if no one has read the problem, I have the actual problem here. Give you guys a couple minutes to read it out.
How many of you have not seen this problem before? Yes. You haven't seen this before? Have you? You read the constitution, no? I think there's only one person. You want to
Okay.
summarize the problem?
Yeah, I got it in the next slide. So you're basically given a string of up to 100,000 characters, and we could only use the characters A through Z, both lowercase and uppercase. Now we want to find the number of subsequences that they're called I love strings. Basically, they have a length of 5. They start with a vowel, so everything except the Y. And then we alternate between consonants and vowels. And there's another special characteristic is that each character is pairwise distinct. And we can also have A repeated twice. The only thing is that one has to be lowercase and one uppercase. So at the bottom we have examples. So I love is an I love string, and then IXOXO. I mean, this doesn't seem like it's an I love string, but like I said, you can have X as long as one is uppercase and one is lowercase. Okay, so what's the obvious approach? I can ask you guys, how can you solve this problem? If anyone has any thoughts?
Take every possible set of 5 characters and try them out.
Yeah, that's it. That's the brute force approach.
Yeah.
And what's our time complexity for that? Since we're n choose 5, so we can check every string in pretty much constant time. And then we have n to the 5th solution. It isn't that great. We've started off with worse. It's still polynomial, but still pretty slow. Okay, so
Because n is 100,000, you said?
yeah, n is 100,000. So let's first look at a simpler problem. What if we can have pairwise distinct characters? We can have A, B, A, B, A. Then we can have a simple code, which basically, like Dr. Giri said, we can basically pick every subsequence of length 5, and then we can do this recursively. Once we basically have picked 5 characters, we check if this is an I love string, and then we add this to the answer. We just have to count how many of these are possible. We don't have to print them out or anything. They'll be too big. In fact, one little nuance is that they tell you we want modulo, I think it's 1 billion plus 7, so it's going to be a very huge number. So how can we optimize this? Do we have any thoughts on this idea? We can actually take our previous code. How can we improve it? Demo?
Is it possible to use memorization to solve the subproblem?
Memorization? That's a good idea. How would you do it?
Like, see where you made those two recursive calls. Start a value of the position,
Mm-hmm.
the current index, and then you make another call at that current index if you've already calculated the value, then you just return the values.
Yeah, pretty much we can always take our recursive solution. We can just add a memorization, and we basically solve the problem. The only issue with this is that, let me see. Well, here I explain how it's done. Let's say we have a given substring, ABA, at some point. We have picked these 3 characters, and then we still have these following characters we haven't explored from D all the way to the end of the substring. And we know there's 17 valid continuations of consonant and vowels. Then we just add the 17 and we can stop. We don't have to keep recomputing this subproblem over and over again. Is it the answer? Like, no, it's not. We're not done. We still have that one special property where characters cannot be pairwise. They have to be pairwise distinct. So our solution is actually a little bit complex. So we can still use DP. The only thing is that we're going to make our DP state based on the characters themselves. So basically our DP is what's the optimal solution from up to I with using a vowel 1, consonant 1, vowel 2, consonant 2, and then vowel 3. So we can actually just map the consonants to a number from 1 to 10.
So that's the exact vowel that you're using there?
This is not the final solution, but basically A will map to 1 and then E to 2. But we show the deep.
What is I? I is the?
I is the position of the string.
The position where you're currently at.
Yes. Now, how many possible states can we have? We can actually have this many states. So we're pretty close to working a complete solution, but we're not quite there yet.
How do you get 10 to the 3?
So, okay, so there's 10 possible
Oh, wow.
vowels,
Yeah.
and then there's 42. So actually, in fact, it's actually 11,
20, yeah.
and then 43, because we can have a character that's empty, and we have to represent this in our DP state. So how can we actually optimize this? We do have some redundancy. We don't have to store every single vowel and consonant. The final ones at the end don't have to be saved. So we can actually save this amount of states. And we can basically go down to 10 to the 5th times 10 to the 2 times 42, which is around 420 million. This is very doable. And here we actually show the DP state. All the way at the top, let's say we're at a certain position and we have solved this problem for all j less than I. Then we can say we have 2 cases. We can either take this position and we can add it and use it, or we skip it. So the first case, dp of I, j, k, l, s is equal to dp of I minus 1, j, k, l, s for all j, k, l, s's previous to this I. This is basically just us not choosing the current value.
So you now changed from the actual vowel consonant characters to the positions, is it?
What do you mean?
So the J
Mhm.
is the first vowel that you used, right, in the string.
Mm-hmm.
It's the position, not the actual vowel.
No, it's the actual vowel. So
but then you said J is a number.
we map the vowels to numbers. Basically, 0 will be, we haven't picked it. 1 will be A, 2 will be E, 3 will be I, so on and so on.
Oh, that way, I see, okay.
And then let's say we do pick this character at I,
Yeah.
then we have a case of it could either be a vowel or consonant. And then from this, we split it on to 3 different cases. Yeah.
So then I don't understand what you mean by j less than I. Oh, you mean, oh.
Oh, no, I meant, sorry.
Yeah, you mixed up.
Yeah, ice.
All right.
So let's say we have case 1 where we're starting a new string with this vowel that we use. The DP is just DP of I, V. The zeros represent empty spots. Basically, we haven't chosen this spot anymore. Case 2, we can continue a string of length 2. Again, this one's pretty easy. We just choose. We don't have to worry about a pairwise distinction yet. Or do we? Yeah, we actually do. Sorry. So we have to make sure V2 and J are not the same, because this actually implies that we're choosing the same character twice. We can continue a string of length 4, and we have to make sure that V3 is not equal to J, and L is not equal to J for all J, K, Ls. Again, this is basically checking that the vowel that we pick for the continuing the 4th position does not conflict with the first vowel or the second one. Then we have the case of a consonant. We can continue a length of a string of length 1. Again, there's no pairwise distinction here, so it's just simply taking this previous state. Or we can continue one of length 3. There's actually a mistake here. You want to make sure it doesn't conflict with the first consonant we picked.
So I'm a little bit confused with the plus equals. Why are you doing plus equals?
So plus equals just because we have to make sure we keep track of the not choosing this character. So that's what we do in the first line.
What is the value you're storing in this memoization?
This is the amount of strings with this state. Basically, the states
this
are
particular vowel in the first place, this particular consonant
in the second place,
et cetera, et cetera.
et cetera, et cetera.
And if there is more than one, what are you doing?
If there's more, what do you mean there's more than one?
So what are you counting? I'm still so.
I can write it out.
Yeah.
It's probably much better.
Because if there is more than one, you don't need to count it, right?
Yeah.
Right.
So let's say we have a DP. We say I.
Yeah.
Basically, let me just make a string.
Right.
A, C, B, F, E. This is position I.
Yeah.
Position J represents the first vowel in our string.
Right.
So vowel 1.
Yeah.
And this maps from value 0 to basically, is it 11? I believe so. 0, 1, 2, 3. Yeah. 0.
There are only 5 vowels, so 10.
0 is the first value that we're not counting.
Okay, so it's 0 to 10 then. Right? A, E, I, O, U is 5, and then A, E, I, O, U in uppercase, that's 10.
Yeah. Okay. So 0 means no character, which is empty.
Right.
All the other ones map to a certain vowel.
Okay, got it.
Our next state is a consonant. Let's just call this K. Again, this goes from 0 to 42, 0 being empty. We have to store our next vowel for sure, the second vowel. So we'll call this vowel 2. I'm going to call this L. And same characteristic as this vowel.
Yeah.
This state is a special one because it represents a consonant.
Yeah.
But we don't actually have to store every single one. We just have to say, have we picked it yet? So it's either 1, 0, or 1. One of these two. 1 represented we picked it, and 0 represent we haven't picked it. And we could make another state, but we don't even have to. When we're actually choosing a string of the length 5, we just have to check this state and then add it to a global counter.
This tells me how to, what the dimensions, what the coordinates of my entry are, but what goes into the entry?
So that's those cases. But I can write, I guess, one of them.
Is it a number? It must be a number because you're counting.
Yeah.
So
We
it's a
also
count of what?
we start with the actual string of length 0. There's only one way to make this string.
Yeah.
And from this, we continue it. So there's only one way to make the string of length 0.
Yeah.
I'm going to call this one way. And then let's say we have our first character is A.
Yeah.
So we can actually continue this string and create string A.
Yeah.
And there's only one way to do this.
Okay.
Now we go to C.
Yeah.
We can either choose to not count A, or we count A and continue with C, which we can. So now we can add C, and then we get AC.
Yeah.
Or we can choose to start a new string. We can't even choose to start a new string, because we have to start it with a vowel. So at this point, this is all we can make. We can go to B, and then we can choose to, we can't continue this state. We can't even start a new state. But we can continue A. So we have AB.
Right, but the AC goes into a different entry than AB, right? Because
Yeah,
the coordinates are different.
coordinates are different.
So in that entry for AC, what are you going to put?
For AC, I'm only going to put 1. There's only one way to make this at this length.
When will it ever become 2? I don't quite follow.
Oh. How can I think of this a case? So let's say we have this AC,
Yeah.
and then we have X. At this point in time, we have 2 ways to make AC. So DP at 1, 0, 1, 2, 3, 4, 5, 6. At 6, I'm going to just use the characters. We can think of them as numbers.
Yeah,
But
forget the quotes, just say AC. Yeah.
equals 2. So at this point in time, we have 2 different ways to make AC.
But why do I care whether it's 2? Because I can only use one of them.
But we can actually, no, we can use 2 different ones.
How so? You can't allow repeat, so how can I use them?
Well, we're talking about subsequences.
Yeah.
So this is one subsequence and this is 2.
Right.
If we choose to continue it with E, we can have 2 different ways of making ACE and ACE here.
But they can't be counted separately because they'll end up as the same strings.
They can be counted separately because there are different positions.
Oh, where did you say that?
I can go to the beginning.
I didn't realize that was allowed.
Let me see where it says it. I guess you can look from the example I love with 3 O's.
Yeah.
We can have I love 3 times.
Oh, I see. Because each of those O's gives you a different
I love.
position that you're choosing. Oh. No, I didn't see that. But none of the rules seem to directly address this. The number of subsequences of the string that form that kind of string, although it's not, it just okay, so it's considered a different subsequence. That's
Yeah.
your point. Okay, got it. Okay, next.
So
Alright, now
what
I
was
get
it?
So you're counting
So
how many ways you can pretty much end up with the same string
at this certain position.
at a certain position. Okay.
And we break this idea down into these 3 main cases and then the 2 other cases.
Right,
and then
because, yeah, uh, depending on which coordinate you're looking at, you'll get a slightly different number, right?
for the final answer, we don't have to store this as a DP because we're not continuing this length of 5. We can just add it to our final counter. Answer is basically a global counter. We just keep track of the answer. And it basically means this state corresponds to we have a length of string 4 that is valid. And now we have this next vowel. We just have to check pairwise distinction with the other vowels, and we're done.
So you're gonna add up all the entries where the 4 coordinates are not 0. 5 coordinates, 4 coordinates are not 0. Is it?
1, 2, 3, 4, 5.
Well, the fifth one, the first one, you know it's not going to be, oh, I see, fine. First one can be for any position.
The first one, we just have to look at the previous position.
But you have only 4 positions after that, so, because the fifth one you don't care.
I don't care. I only have to look at the previous value.
So if the O at different positions are considered different characters, but we still don't allow it being used in the same word.
Not in the same word. We can have.
But it can be in different ways.
Does that make sense to everyone here, or?
Yes? You lost him somewhere? Go ahead, drill it.
I can explain it in a more intuitive sense if we look at the recursive
Go for it.
idea. Basically, like Demba said, let's actually try every possibility. Let's start with I love. Now we can choose, we're at position I. We start there. We can choose to take this I character or not. On the left side, we'll take it, and on the right side, we won't. For this side, again, we're in L. Now we can choose to take it or not. It actually depends on if we can continue this I love sequence. We can actually check it in constant time. So since it's I and it's L, we can continue it. So we can have IL. Or we can just skip it and stick with I. I'm going to just keep going down the left subtree until we kind of finish. ILO, we can continue. For the next character, we can't really choose it. We actually can't choose the next 3. So I'm going to just skip to VE. I love. Now for this tree, since we skipped O, we still have ILO, and we can make I love again after some certain number of moves.
That would be using the second O.
That's using the second O. So this possibility, this our first initial code, we can think of the DP state as the actual string itself. If you want to store it in some sort of maybe like a set, that will be part of your DP. The only thing is that this has a lot of overhead because it's just not as quick as a DP table. It wouldn't run, but it's still good to try it this way. Does anyone have any questions?
One of you wants to go and explain it?
And I do have my code up in GitHub if anyone wants to see it. I recommend you try doing it first yourself. First, try doing the simpler problem where we can have characters that duplicate. See if you can finish that, and you can go from there. Yeah. Let me just double check. Like you're talking about this, 1 to 10? We can use, so we have a distinction between lowercase a and uppercase a. So we have to multiply by 2. So we can keep track of whether it's a lowercase or an uppercase in our state. So there is that distinction. And like I said, 0 will count as an empty character.
Very cool. Okay.
And yeah.
You got that all captured? Still has 10 minutes. Thank you, Ricardo. So we have 10 minutes. Is there a request for any problem that you want to see?
Do we want to go over team forming for those things?
Which one?
Team
Team formation. Yeah, that's a good idea. You sent me suggestions. I don't remember them now off the
Yeah.
top of my head.
So Ricky, then was me, and
Yeah.
then I know Joseph and David and Clement. But you guys have any?
You guys going to compete with us on March 5th? It's really exciting. And there's food. Sorry? Well, you go there for the experience and then train for the next time. That's the plan. Sound okay? All right, you committing to March 5th? It's pretty much a, it's a 5-hour competition, and you need to be there. Yeah? You, sir? What's your name?
Carlos.
Carlos.
No.
No? Sure?
Yeah.
Why? If I may ask.
I
Why
didn't-
not?
I didn't get this.
You don't have to get, look, you're part of a team. Your job is to try and solve, let's say, 2 problems out of the 10. If you can solve 2, you'll be fabulous. Your team would the others would take on other problems, and your team would be superbly successful.
I think that is during spring break.
It's an all-day affair on March 5th.
The whole day.
Yeah, set aside the whole day.
It'll be in that big, right?
It's across the street.
Yeah. Wait, it's not here?
Sorry?
It's not here downtown?
It's in PG5.
Oh, 5 or 6?
What is it across the street? PG6?
Yeah.
Okay, 6. Tech station. Yeah.
Oh, okay.
Good. So we'd have to make teams for the. Can you send a message and see who else wants to?
I'll send
Wants to.
messages, and if David can announce it on your lesson as well.
Oh, yeah.
'Cause I don't get
So what I suggest is we should try and form at least 4, maybe 5 teams if possible, and go there in full force and see what happens. Yeah.
question.
Yeah.
Are we all competing Division 1 or?
That's a good question. Yeah. It turns out you could break up some teams into Division 1 and Division 2, but then the Division 2 don't get scored. I think something like that. There were some strange rules. In the recent past, we've just competed in Division 2, and there's better chance that you'll you'll make it to the top 3. Division 1 is quite competitive, but there aren't that many teams that are super competitive. The 2 top teams are UCF and Georgia Tech. They are just unstoppable. They've trained for decades now, so they're very strong. They have 6 coaches. Here we have 1 measly coach.
Best coach. Our favorite coach. Yeah.
So it's hard to compete against them now, and they field 10 teams. So it's like they come in full force. So Division 1 is really quite challenging, but that doesn't mean you shouldn't do it. There is one of the prizes. One of the prizes is for the top 3 schools that make it to whatever. So if we come just after Georgia Tech and UCF, I think we should be pretty proud of ourselves. So if you go for Division 1, we could try and get this team prize or this university prize. On the other hand, if you go for Division 2, 3 years ago our team won the 2nd place. You would have a pretty good shot at that. So I'll let you guys decide. For me, it's fine either way. I love the competition, and I love the whatever the adrenaline rush. Even watching it is fun for me.
So how do you qualify for to go
Division 1 or
level?
to the next level? You have to be in the top. Oh, that's a good question. I've forgotten the rules, so I'd have to check this up. Yeah, because you're saying that might decide what we want to do. If Division 2 doesn't help you to go to the next round, why bother?
Yeah, exactly.
That's a good point. Let me take a look at it this evening, and we can decide. Yeah. I think Division 2 doesn't qualify to go to the, well, essentially the next round, earlier the next round was just the World Finals, which would take you to who knows where. But now I think there's an intermediate round somewhere in North America, which is still fun. You would still go someplace interesting and compete. And I think there are maybe 3 teams or 4 teams from each division, each region that goes there. So I would assume it's the top 3 schools from Southeast region that ends up sending a team there. That's my best guess. So Division 1 top 3 team could be really quite a lot of fun. So after UCF and Georgia Tech, who look unbeatable at this point, the next teams to compete with for you guys is Florida Tech, which has a pretty decent team, UF, which is erratic. Sometimes they have strong teams, and then occasionally there's Clemson. I think these are the only 3 teams to kind of look out for. Sorry?
We did good against Clemson.
Yeah, you do pretty well against all 3. So yeah, if I were you, I would try to shoot for the 3rd best university team or something. That's what I would suggest. But then if one team wants to be in Division 1, I think we have to put all of you in Division 1. The problem sets are a little bit harder. So for beginning teams, it's a little more discouraging. However, I think I saw a rule that said that we could send some teams to Division 2, except that you won't get listed and get credit for doing really well. If you don't care about that, and if you're there just for the experience, like I was saying, then Division 2 might work out, and I can let you know about that. What do you think? So you want to go for Division 1?
Depending
On the rules,
on the
rules for the
yeah.
next level. Okay.
The best goal I find in mind is I want to get to the top and hopefully proceed if possible.
Yeah, yeah. Okay. Teammates, that sounds okay to you?
Let's do it.
Okay. You guys, your team, Division 1?
Clemson, no, Clement,
Yeah.
Joseph, and yeah, the three of them.
Also go for Division 1?
Yeah.
Cool.
We'll try
Okay.
that.
All right. And you guys can choose later, but I would say there's only, what, 3 weeks left, so put in what all you've got and give it a shot. That's what I'd say. Yeah? It's the tournament is fun. The competition is just a lot of fun. You all sit in this big room, and you get to sort of see the scoreboard, so you know who's solving what, and you know the energy there is something else. Yeah. Okay. All right. So we probably are out of time already. I have 1 minute, so let's see if I can. Right, so have you guys seen this problem?
Yeah.
And?
That's the one where it's like 3D, right?
Yeah. You've looked at this? No? You may have looked at it?
May have looked at it and was intimidated.
All right, so the problem, let me explain the problem because we don't have much time. We can't sit and read this, unfortunately. So you are sitting in this spaceship somewhere here. Your base station is somewhere there. This is all in space. And there are a bunch of other ships that are chasing you. Fortunately, all you have to do is to get there, to the base station. So this is the base station. This is you. So all you have to do is to get from here to here. However, there are a bunch of asteroids that are running around here. Okay? And if any of these come in your path, you're dead meat. You're not going to make it there. So what you're given is the coordinates of you, wherever you are right now, the coordinates of where you want to be, the base station, each of the asteroids, and their directions. This is what you're given. And you're asked, are you going to make it alive? Yes or no? That's the question. So what does this problem need?
Quick question, just to explain the problem. So when you say get in your path, it means like hit you while you're moving, or just be in your direction?
Right. So the problem has some weird things. It says that you can head in that direction, but your engine is kind of shot and you don't have any control over the speed. So the speed is erratic. It could be slow, it could be fast, you have no idea. And the same thing with each of these asteroids. Their speeds are their speeds. It could suddenly change or whatever. We just don't know. All we know is the direction and their location.
Asteroid can speed up.
Sorry?
An asteroid can speed up.
Asteroid can speed up too, I think, yeah. Isn't that true? The asteroids can rotate, and you don't have any, where did I see that? See, at an unknown speed.
Oh, okay. So you don't know the speed of the
You don't know the speed,
Oh.
but it'll never move backwards. So what is it that we need to do here? There are a few other things that I haven't told you, but we'll get to that in a minute. Yes, sir.
Just to make sure I understand the question.
Yeah.
So you're moving to the base, right? You don't know what your speed is, and there are a bunch of asteroids that
Right.
hit you, and you don't know what their space is.
Right.
The only way you can avoid you don't get hit is if you're moving at a different direction, because you guys are if the directions can collide at some point, you don't know.
That's
you
it.
don't know anyone's speed.
You're absolutely right. So all you have to figure out is, do any of the asteroids, do any of the paths of the asteroids intersect your path directly to the base? If it does, since we don't know the speeds of any of these guys, it's a danger. You may not make it. Okay? So the only way you can be sure you're going to make it is if none of the asteroids intersect your path. So therefore, the only thing you have to figure out is, given two lines, do they intersect in three-dimensional space? All right? And we'll talk about that next time. That's all the problem here. Well, there is one other little detail. You're told that your ship is tiny, and these asteroids are monstrous. Okay? They're a huge boulder that's much bigger than your spaceship. And each asteroid is a piece of rock that's has a polyhedral shape. You're given the center of mass, and you're given the coordinates of its convex hull in 3D. Okay? So it sort of looks like a golf ball, where you're told where the center is and what the coordinates of each of the sharp points are. And that thing can rotate on its axis and do whatever stuff it can tumble, and so you have to make sure that this sucker doesn't hit you with a glancing blow. So what do I do there?
So since they could rotate, we can assume to it to be like a circle, and we want to make sure that they line up that way.
That's right. So what we're going to do is we're going to figure out the distance to each of its points, find the farthest one, and make a sphere with the farthest one. And assume that the asteroid is a ball that looks like that. And so we'll forget all the convex hull. We'll just think of it as a ball. And then now what we have to do is to make sure that when it passes, the shortest distance between this line and this line in 3D space. Remember, 3D space, they don't have to intersect. Not all lines intersect. They can go like that. You want to find the closest distance between these lines. And wherever it comes, the closest distance between the lines, you want to make sure that this is smaller than the size of the asteroid. Does that make sense? If the asteroid gets close enough that its radius can hit you, you could be in trouble. So we're going to take each of the asteroid paths, find its closest distance to our main path, and check if that distance is less than the radius of this ball. That's what we have to figure out. Yeah?
The reason we don't want any intersection between our spaceship and the base is because of that unknown speed.
Exactly. I don't see any other way to handle it. So in the end, your problem is, this is easy to handle. Your problem is, given two lines in 3D space, find the closest distance between these lines. That's what we're going to look at next time, and we'll have solved the problem. Cool?
Does it like have a smart solution like that, the 2D one, the clockwise?
In 2D, two lines always intersect.
Oh yeah, at some point they will intersect.
Yeah. So in 2D, it's almost trivial. If you don't know the speeds, you're going to get hit. Well, there is one thing you could do. there is one thing here that you have to worry about, because it's possible that that even though this line does have a very close distance, it's possible that this asteroid is moving in that direction. So you do have to check that it is moving towards your line and not away from it. But other than that, I don't see any other way you could do any shortcuts. Not that I know of. You could look at it some more. Okay? It's not hard. We're going to use vector algebra to try and figure this out. It all reduces to something reasonably simple, which you can also apply to 2D if you want to. Yeah.
Is there like a smarter way of knowing whether it is going your direction, your general direction? Because let's say it might be
Yeah.
going towards you, but it might be going before where you started, and at that point you don't really care.
Yeah. For that, you could look at the current distance from this point to the line and see if it's decreasing or increasing. If it's decreasing, then you know that it's going towards the line. If it's increasing, it's going away.
But what if its direction is right behind you?
Think of two lines like this. Okay, if it's coming from my shoulder,
yeah.
then clearly it's going towards the line, and the distance is going to reduce, and then it's going to increase.
Oh, okay, later on.
Right? There is a point where the line that the shortest distance is going to be perpendicular to both lines, and that's the point that we're trying to find. Clear? Okay.